Hello and welcome. Today we're digging into one of the most important and misunderstood pieces of blockchain infrastructure, Oracle services. If you've ever wondered how a smart contract knows the price of ETH, who won last night's game, or whether it rained enough to trigger a crop insurance payout, the answer is almost always an oracle. Here's the big picture. Blockchains are deterministic machines. Every node must see the same inputs and compute the same outputs. Or consensus breaks. That means chains can't just call a web API like a normal app. Oracles bridge that gap. They attest to off-chain facts and deliver them on-chain in a way that's auditable and predictable. Without them, most of DeFi wouldn't exist, and many real-world use cases would be impossible. But there's a twist. Oracles introduce risk, big risk. Look across incidents in lending, derivatives, and stablecoins, and a pattern emerges. Oracle design sits right alongside smart contract bugs and bridge failures as a top 3 source of systemic risk. And decentralization alone doesn't save you. The protocols that survive volatility engineer their Oracle choices, integrations, and monitoring with ruthless attention to detail. Oracle risk is technical, operational, economic, and strategic. Let's start with why oracles exist. Consensus requires consistency. If nodes could make arbitrary HTTP requests, you'd get non-deterministic state and easy manipulation. The Oracle problem is how to bring external data into a closed, adversarial system without compromising its guarantees. The term Oracle comes from ancient intermediaries delivering messages from the gods. In crypto, oracles carry messages from the real world into smart contracts. How do Oracle services differ? First, centralized versus decentralized. A centralized Oracle is run by one entity. It's fast and simple, fine for a low-stakes app or MVP, but it creates God mode risk. If that operator is hacked, bribed, coerced, or makes a mistake, your entire protocol is exposed. Decentralized Oracle networks, or DAWNs, spread trust across multiple nodes and sources. They aggregate values using robust statistics, often a median or weighted median, so one bad input won't swing the result. Using medians, these networks can tolerate a large fraction of faulty inputs and still land on a correct answer. That's why they secure billions in DeFi. The trade-off is more complexity and a different set of liveness and incentive questions. In return, you get redundancy and far lower single point of failure risk. Next, push versus pull. A push oracle posts updates on a schedule or when a price moves beyond a set deviation. Contracts read the latest value, predictable. Low latency reads and easy gas budgeting. Downsides, predictability can be gamed, and during congestion, feed freshness can suffer. A pull oracle flips it. You request fresh data when needed. It's computed off-chain, then posted back. You can get up-to-the-minute data and even cryptographic proofs about when it was fetched. But you introduce request-response latency, and the fulfillment transaction can be exposed to MEV if not handled carefully. Inbound versus outbound is another axis. Inbound oracles bring facts onto the chain. Prices, weather, sports outcomes, identity attestations. The vast majority of usage today. Outbound oracles push actions off-chain when something happens on-chain, triggering a shipment after escrow release, or notifying a reporting system when a threshold is crossed. This is where digital meets physical, and it's a likely frontier for innovation. What's the best type of oracle? It depends. A high-frequency trading platform cares about latency and update predictability very differently than a parametric insurance protocol that needs tamper-resistant, verifiable weather data. Good oracle design is about aligning trade-offs with your risk profile. How does Oracle data get attested? Aggregation-based. Query multiple independent sources and combine them, filtering outliers with robust stats. This is battle-tested for price feeds. Independent errors cancel out. Coordinated manipulation stands out. Trusted execution environments. Secure enclaves like Intel SGX or ARM-based solutions fetch and process data inside a testable hardware, proving a specific program produced the output. This reduces some manipulation surfaces, but introduces a hardware trust assumption and potential side-channel risks. In practice, teams often combine methods and add cryptographic commitments to attest to freshness and integrity. Where do things go wrong? Common risk patterns. 1. Single points of failure. Relying on one operator, one data source, or one chain for relays creates fragility. If that piece goes down or is compromised, everything depending on it can cascade. 2. Timing and predictability. If everyone knows exactly when a feed updates, sophisticated actors can position around those moments. Stale updates during congestion can cause mispriced liquidations and bad debt. 3. Data quality and source manipulation. Thin liquidity, wash trading, or sudden gaps can distort spot prices. Pulling from a single DEX without safeguards invites trouble. 4. MEV exposure in pull workflows. If a fulfillment transaction carries valuable information, it can be sandwiched, censored, or arbitraged unless you use private routing or commit reveal. 5. Incentive misalignment. If Oracle nodes aren't economically aligned with protocol safety, bribery and collusion risk rises. Without slashing, reputation, or performance-based rewards, poor performance persists. 6. Integration mistakes. Wrong decimals, scaling errors, missing sanity checks, or misconfigured deviation thresholds can make a good Oracle look bad and cause losses. 7. Governance and operational risk. Who can change feeds, update parameters, or pause the system? If a small group can flip a switch without controls, you've shifted risk from code to people. So what actually works to reduce these risks? Here's a practical playbook. Use decentralized aggregation for high-stakes value. Favor medians over means, insist on independent sources, and understand the node set and incentives behind the network. Tune parameters to your asset and use case. Set heartbeats and deviation thresholds that balance freshness with noise. High volatility assets need different settings than stablecoins. Don't copy-paste. Add sanity checks and circuit breakers. Bound acceptable prices relative to historical bands or reference markets. If a price jumps beyond a threshold, require multiple confirmations or pause sensitive functions like minting and borrowing until reviewed. Consider smoothing. Time-weighted or exponential moving medians can dampen transient spikes without masking genuine moves. For liquidations, short TWAPs or median of medians reduce false positives. Use multiple feeds or fallbacks. Cross-check a primary feed with a secondary reference. If the primary stalls or deviates too far, switch to conservative mode. Raise collateral requirements, slow liquidations, or pause new positions. Harden poll workflows against MEV. Use private mempolls or commit reveal for fulfillment. Add randomness to update times and avoid broadcasting sensitive requests in the clear. Plan for liveness under stress. Simulate congestion and reorgs. Ensure updates can land when gas spikes. Build alerting for stale feeds, missed heartbeats, and abnormal deviations. Maintain an on-call runbook and emergency powers with clear, auditable procedures. Lock down integration details. Double-check decimals, scaling, and rounding. Make feeds immutable at the contract level where possible. If upgradability is required, protect it with time locks, multi-sigs, and public notice windows. Align incentives. Prefer providers with transparent economics, performance histories, and penalties for bad behavior. If running your own network, design slashing or reputation that rewards uptime and accuracy. Monitor like your life depends on it. Dashboards, alerts, postmortems, and drills. Treat Oracle monitoring as a first-class SRE function. Here's a quick checklist to take back to your team. Define exactly what data you need, at what precision, and how often. Choose centralized or decentralized based on value at risk and time to market. Decide on push or pull depending on latency and MEV concerns. Document heartbeat and deviation settings. Implement bounds, circuit breakers, smoothing, and fallbacks. Test in chaotic conditions, high volatility, gas spikes, and reorgs. Secure governance with time locks, multisigs, and clear emergency procedures. Set up 24/7 monitoring with alerting and escalation paths. Let me leave you with this. Oracles are the connective tissue between code and reality. They unlock new categories of applications, and they're not going away. The difference between a protocol that weathers a storm and one that gets wiped out is rarely luck. It's disciplined engineering, thoughtful trade-offs, and relentless operational readiness. Build for the day when everything goes wrong, and you'll be ready when it does. Thanks for listening. If this sparked questions, keep exploring. The more you understand Oracle architecture and risk, the stronger and safer your applications will be.